Imagine a silent, perpetual war raging inside you right now. Every single second, really, an unseen army is standing guard, defending microscopic borders, launching surgical strikes, and remembering every battle it's ever fought. Most of the time, you don't even feel it. What incredible, intricate system is this, protecting us without us ever having to consciously lift a finger?
That remarkable, tireless defense is orchestrated by our immune system. And it's not just, a collection of cells. It's a highly sophisticated, multi-layered, and incredibly dynamic network of specialized cells, tissues, molecular machinery, constantly at work.
Like your body's own personal security force.
Exactly. Think of it just like your body's personal, highly adaptable security force dedicated entirely to your survival.
Today, we're taking a deep dive into excerpts from The Invisible War, our immune system's battle against viruses. Our mission today is, well, to pull back the curtain on this cellular war, deconstructing it from the very first attempted breach of our outer defenses, through the rapid alarm systems, to the mobilization of elite specialized forces, and finally, to the establishment of long-term memory. We want to give you a shortcut to being truly well-informed about this incredible microscopic world inside you, a world where vigilance is constant, and frankly, the stakes are life itself. So let's unpack this journey. Before any cellular warfare even begins, before the heavy artillery is called in, what are our very first lines of defense? Our physical and chemical barriers, right?
Exactly.
These are the fortified outer walls of our internal castle, sort of designed to keep the vast majority of threats out.
Precisely. Our body's internal environment, this incredibly rich and stable ecosystem, is separated from the chaotic outside world by what the source accurately calls formidable physical and chemical barriers. Think of them as the initial non-negotiable checkpoints, the castle walls, the moats, the sentries, all working to keep most invaders out before the real fight for internal control even starts.
And when we talk about physical barriers, we're talking about something as obvious yet as complex as our skin, aren't we? It's far more than just a wrapper.
Absolutely. Your skin, the largest organ, is a truly remarkable barrier. It's composed of multiple tough, keratinized layers of cells that are constantly being shed and renewed. This continuous turnover makes it incredibly difficult for pathogens to establish a lasting foothold.
It's dynamic.
It's not just a static wall, it's a dynamic, self-renewing surface. But beyond the skin, consider the mucous membranes. These line all the body cavities open to the outside your respiratory tract, digestive tract, your genital tract.
Right.
These membranes are moist and sticky, producing mucus that physically traps inhaled or ingested pathogens, preventing them from directly reaching and binding to the underlying cells. The cilia, those tiny hair-like structures in your respiratory tract, then actively sweep this mucus and any trapped invaders out.
Pushing them away.
Exactly, often to be swallowed and destroyed by stomach acid or expelled by coughing and sneezing. It's quite effective.
It's a brilliant, multi-pronged physical blockade. But you also mentioned chemical barriers. What kind of chemical deterrents are actively working, to disable invaders before they get too far?
That's a critical second layer of defense. We have incredibly potent acidic secretions. For example, your stomach acid has an astonishingly low pH, often between 1.5 and 3.5.
Wow.
Which is acidic enough to denature proteins and effectively destroy most pathogens swallowed with food. Even your skin maintains an acidic pH, known as the acid mantle, which is inhospitable to many bacteria and viruses.
So even our skin has this chemical shield.
It does. And then there are enzymes like lysozyme found abundantly in your tears, saliva, and mucus. Lysozyme is like a microscopic molecular scissor. It specifically breaks down the peptidoglycan cell walls of bacteria, and while its primary action is antibacterial, it can also interfere with certain viral structures, offering another subtle but important layer of protection against a broad spectrum of threats.
It's truly astounding. Every time you feel a small scratch or you notice the protective mucus in your nose doing its job, or even just tasting the natural enzymes in your saliva, you're experiencing active parts of this initial defense. It's not passive. It's a living, breathing, constantly regenerating, and chemically active barrier system that's, incredibly effective most of the time. So these physical and chemical barriers are phenomenal. But of course, the microscopic world has its master strategists. What happens if a virus does get past these formidable walls? How does something so incredibly tiny begin to take over a cell? This next part, I imagine, is where the real biological espionage begins, right?
It absolutely does, and it's a masterclass in biological infiltration, a prime example of evolution at work. Viruses have indeed evolved countless strategies to bypass our fortifications. Once they successfully adhere to a cell, their ultimate goal is singularly focused: to invade and replicate, to turn our own machinery against us.
So let's use a common example from the source material, like a rhinovirus, which causes the common cold, or maybe an influenza virus. How do they actually execute this invasion? What's that critical first step inside?
Well, let's say a common cold virus or an influenza virus manages to be inhaled and successfully adheres to cells lining your nasal passages or upper respiratory tract. This adhesion is highly specific, often involving viral surface proteins binding to particular receptors on our host cells.
Like a key in a lock.
Exactly, like a key fitting a very specific lock. Once attached, this is the critical moment, the virus doesn't just sit there, it executes its primary function. It has to get its genetic material, its DNA or RNA, inside the host cell.
How does it manage that?
Different viruses have different entry strategies.
Mm-hmm.
Some inject their genetic material directly, others get sort of swallowed by the cell through a process called endocytosis, or they fuse their viral membrane with the host cell membrane. But the result is the same. The viral genome is now inside.
And this isn't just an infection. The source calls it a hijack. What makes that term so fitting beyond just a simple infection?
Hijack is indeed the perfect term because it implies a complete and forced takeover of the cell's purpose. Once inside, the virus literally commandeers the host cell's own molecular machinery.
All of it.
Pretty much. Think of your cell as a miniature city, complete with ribosomes, protein factories, enzymes, the workers, and energy stores, the power plants, all designed to build your proteins and perform your functions. The virus takes over all of it, forcing the cell to stop its normal operations and begin furiously replicating viral components.
Wow.
The cell's no longer working for us. It's been transformed into a factory, assembling thousands of new viral copies. It's crucial to understand this transformation. The cell becomes a puppet, manufacturing units for the enemy.
Our own cell.
Yes, our own cell. And this is why a viral infection can be so devastating, because our own cells are turned against us.
That's incredible to visualize a single virus transforming a healthy cell into a viral production line, spitting out thousands of new viruses, all at our expense. That sounds like a rapidly escalating local conflict.
It is a local conflict that quickly escalates. These newly assembled viral copies eventually burst forth from the infected cell, a process called lysis. Or sometimes they bud off to infect neighboring cells, initiating what the source aptly describes as a rapidly escalating local conflict.
And it happens fast.
Very fast.
Yeah.
This speed and efficiency of the hijack is what makes viruses so formidable. A single successful invasion can quickly lead to widespread local infection, often before our deeper, more specific immune systems even fully recognize the threat, buying the virus precious time to spread. It's a race against the clock for our defenses.
So a cell is hijacked, forced to become a virus factory, churning out thousands of new invaders ready to burst forth and spread, but it doesn't suffer in silence, does it? This triggers the first wave of defense, the innate immune system. This sounds like the immediate frontline response, the first wave of resistance.
It is, absolutely. The innate immune system is our most ancient, hardwired, and immediate defense mechanism. It's what we call incredibly fast, responding within minutes or hours, but also nonspecific.
Nonspecific. What does that mean exactly?
It means it recognizes general patterns associated with pathogens, rather than needing to identify a particular virus by name or specific molecular signature. Think of it like a general alarm system that goes off when any intruder is detected, without needing to know their specific ID badge or the color of their uniform. It's about recognizing danger broadly.
Okay. And how does that alarm actually get sounded? Does the infected cell just scream for help? How do our other defenses know that a breach has occurred?
In a way, yes, it screams for help. The first cry for help comes directly from the infected cells themselves and also from nearby immune cells, like macrophages, in the form of signaling proteins called interferons.
Interferons, okay.
These molecules are a crucial alarm system, a chemical beacon that serves two vital purposes. Firstly, interferons warn nearby uninfected cells to activate their own antiviral defenses. They essentially tell those cells, danger is coming, prepare for invasion.
Like putting up shields.
Exactly, by inducing the expression of hundreds of genes that encode antiviral proteins, making those cells much harder for the virus to infect. Secondly, they act as a chemical beacon to attract other immune cells, the immediate first responders, to the very specific site of invasion, escalating the local response.
So the infected cell, even as it's being exploited and used as a viral factory, is sending out an urgent warning to protect its neighbors. It's an incredible act of cellular altruism, isn't it? Like a smoke detector in your house, not just sounding an alarm, but also calling the fire department and telling your neighbors to prepare.
That's a great analogy. It's like a town crier alerting the entire village. Danger is here, and it's specific to this threat.
Who are these first responders, these brave soldiers drawn by the interferon beacons to the site of infection? Who's leading the charge in this initial chaotic skirmish?
Among the first and most crucial to arrive are two key cellular players in the innate immune response, macrophages and natural killer, or NK cells. Macrophages are aptly named big eaters, derived from the Greek for large devourer.
Big eaters, I like that.
Right. These are large, long-lived phagocytic sentinels that constantly patrol our tissues. When they arrive at an infection site, they are incredibly active. They literally engulf free-floating viruses and cellular debris, acting as the tireless cleanup crew, but also as initial attackers.
So they do cleanup and offense.
Yes, they identify and swallow up pathogens, infected cells, and the remnants of dead cells, preventing further spread and clearing the battlefield.
So macrophages are kind of like the general infantry, clearing out the immediate threat and tidying up the mess, but also serving as an initial line of attack. But what about natural killer cells, NK cells? They sound a bit more specialized, perhaps a bit more ruthless.
NK cells are fascinating. And yes, ruthless is a good word for their efficiency. They are cytotoxic lymphocytes that don't need specific training, unlike some other immune cells we'll talk about. Instead, they operate on a principle often called missing self.
Missing self?
Yeah. Healthy cells proudly display specific proteins on their surface. These major histocompatibility complex, or MHC class I proteins. It's like an all-clear signal, basically saying, I am healthy and belong here.
Like showing ID?
Exactly like showing ID.
Yeah.
Infected or cancerous cells, however, often downregulate or lose these MHC class I markers, and they might also start displaying specific stress signals. When an NK cell encounters a cell that's missing these MHCI signals or showing those stress markers, it flags it as suspicious, as potentially compromised.
Like a bouncer spotting someone without the right ID.
Perfect analogy. And then, yes, it forces them to undergo apoptosis programmed cell death.
This raises an important question, though. Why would our own cells be forced to die? It sounds counterintuitive for our body to destroy its own components.
It's a vital strategic sacrifice. Apoptosis isn't a messy, inflammatory explosion like necrosis. It's a neat, controlled cellular suicide. The infected cell systematically dismantles itself into digestible packages.
Containing the damage.
Precisely. Preventing the virus from completing its replication cycle and spilling out its viral payload to infect more neighbors. NK cells are like the special forces that surgically eliminate compromised assets. By inducing this controlled death, they destroy the virus factory before it can release its thousands of new copies, effectively limiting the spread of the virus.
It's a profound example of the immune system prioritizing the survival of the organism over the survival of any single cell, isn't it?
Absolutely. It's a calculated risk, but essential for containing the threat.
While this initial rapid battle rages with macrophages clearing debris and NK cells neutralizing hijacked factories, there's another critically important role being played: the intelligence officers of the immune system. Who are these unsung heroes, operating sort of behind the chaos of the immediate fight?
These are the dendritic cells, and they play a role of immense strategic importance. They are truly the intelligence officers of the immune system, bridging the critical gap between the rapid, generalized, innate response we've just discussed and the highly specific, powerful adaptive response that follows.
Intelligence officers. Okay. And what's their mission on the battlefield? Are they just another type of scavenger like the macrophages?
They're far more than scavengers. At the site of infection, a dendritic cell will indeed engulf the virus, much like a macrophage might. But its purpose isn't just destruction. Crucially, it breaks the virus down into small, distinctive fragments, which are called antigens.
Antigens, like molecular fingerprints.
That's a great way to put it, molecular fingerprints of the invader. It then takes these fragments and displays them prominently on its surface, using specialized protein cradles known as the major histocompatibility complex, or MHC.
The MHC again.
Yes, these MHC molecules, they come in different types. MHC class I found on almost all cells, and MHC class 2 mostly on immune cells, like dendritic cells, macrophages, and B cells. Their job here, on the dendritic cells MHC class 2, is to proudly display a piece of the invader, essentially presenting a wanted poster of the viral fragment so the adaptive immune system can see it.
So it's not just a cleanup crew, it's collecting evidence and preparing a wanted poster. And then what happens? Does it stay on the battlefield, waiting for backup?
No, absolutely not. That would be a waste of crucial intelligence. Laden with this critical intelligence, this wanted poster of the enemy, the dendritic cell then undergoes a profound transformation and migrates from the battlefield. It travels through the lymphatic system.
That highway network for immune cells you mentioned.
Exactly. That sophisticated highway network of vessels and nodes, all the way to the nearest lymph node. And if we connect this to the bigger picture, this migration is incredibly important. The dendritic cell is literally carrying the enemy's blueprint, the antigen, to the military command center, the lymph node, to plan the next, more sophisticated and highly targeted phase of the war.
It's the critical handoff of information.
It is, moving from a local skirmish to a strategic, body-wide response that will ultimately define the outcome of the war.
So our intelligence officer, the dendritic cell, has gathered the blueprint, the antigen, and is now on the express lane to command central, the lymph node. And this arrival isn't just a destination, is it? It's the trigger for a whole new level of defense, where the immune system starts to get truly specific, where the elite forces are finally mobilized.
Exactly. The arrival of that antigen-presenting dendritic cell at a lymph node marks the dramatic beginning of the adaptive immune response.
Oh.
Lymph nodes are not mere glands. They are described as highly organized military command centers, bustling with activity. These nodes are teeming with the elite soldiers of the immune system. T cells and B cells, each with a unique receptor waiting for its specific match.
Billions of them.
Billions, potentially. And what's truly remarkable is their internal architecture. A complex network of stromal cells and extracellular matrix, which is perfectly designed to maximize the chances of an encounter between that single dendritic cell carrying its specific viral antigen and the rare specific lymphocyte that can recognize it.
It's like an incredibly efficient, high-stakes dating service for cells.
That's a good way to think about it. Optimized for finding that needle in a haystack.
That sheer scale of the search is mind-boggling. Imagine looking for one specific key that fits one specific lock amongst millions, maybe billions of possibilities, but doing it with incredible efficiency within this bustling command center. It's like a biological supercomputer running a complex search algorithm in real time.
It really is a marvel of biological engineering.
So the dendritic cell presents its intel in the bustling lymph node. Who lights the spark that ignites the sophisticated adaptive response that moves us from recognition to full-scale action?
That crucial spark is ignited when the dendritic cell presents the viral antigen displayed on its MHC class II molecule to a vast army of naive T cells. Each of these T cells has a unique T cell receptor on its surface. The critical search is for a helper T cell, specifically a CD4 plus T cell.
Helper T cell, okay.
That possesses a receptor which perfectly matches the viral antigen displayed by the dendritic cell. This specific binding event, along with a crucial second co-stimulatory signal provided by the dendritic cell, is literally the spark that ignites the entire adaptive response.
So it needs both the match and that second signal.
Yes, that co-stimulation is vital. It's a safety check. Without that perfect match and co-stimulation, the T cell won't fully activate, preventing an inappropriate or overly aggressive response against, say, our own tissues.
Makes sense. Once that specific match is made and the helper T cell is activated, what happens to it? Does it become the leader of the charge?
Absolutely. Once activated, the helper T cell undergoes a profound transformation and becomes what the source calls the field marshal of the entire operation. It doesn't just stay put. It begins to rapidly divide, a process known as clonal proliferation.
Making copies of itself.
Exactly. Creating an army of identical helper T cells, all programmed to recognize that specific viral threat. And then it releases a torrent of chemical messengers called cytokines. What's fascinating here is that these cytokines are far more than just messengers. They are the orders of war, orchestrating the activation, proliferation, and differentiation of almost every other immune cell involved in the adaptive attack, from other T cells to B cells. They direct the entire symphony of the immune response.
So these cytokines are essential communication signals, but I remember hearing about cytokine storms being quite dangerous during some infections. You hear about this, right? Like severe influenza or COVID-19. That sounds like a situation where these orders of war go a bit haywire, turning on the body itself.
You're touching on a critical and often deadly point. These orders, while essential for orchestrating a robust immune response, can indeed be a double-edged sword. While a measured cytokine release is vital, a runaway production of cytokines can lead to a cytokine storm. This is a dangerous overreaction that causes widespread inflammation and can severely damage the body's own tissues, turning the immune system's protective efforts into a self-destructive force.
Like friendly fire, basically.
Exactly like friendly fire. Think of it like an army turning its heavy artillery on its own territory, causing massive collateral damage that can lead to multi-organ failure. It's a stark reminder that even powerful defenses need to be carefully regulated. Too much of a good thing, unchecked, can become profoundly harmful. It's the balance, the fine-tuning that's crucial.
Okay, so with the helper T cells acting as the field marshals, sending out their cytokine orders and essentially defining the target, who are the operatives on the ground? Who are the actual assassins that go out and dismantle these viral factories?
That's where our cytotoxic T lymphocytes, often called CTLs or killer T cells, come in. These are CD8 plus T cells, and assassins is a perfect term because they are incredibly precise but also utterly ruthless in their mission, activated by signals from helper T cells.
Following orders from the field marshal.
Precisely. These CTLs are specifically trained to recognize the specific viral antigen being displayed on the MHC class I molecules of infected body cells. Remember those MHC class I molecules we talked about on almost all cells?
Right, the ones showing what's inside.
Exactly. They are constantly sampling proteins from inside the cell and displaying small fragments on the surface. If a cell is infected, it will inevitably display viral fragments on MHC class I.
So, once trained, these killer T cells know exactly what to look for. They're not just generally attacking. And what's their mission once they're ready? Do they stay in the lymph node or do they go out into the field?
They are immediately deployed to the front lines. They leave the lymph node, enter the bloodstream, and travel to the site of infection, where they begin a systematic hunt. Their mission is to efficiently eliminate viral replication centers with a surgical precision.
How do they actually kill the infected cell?
When a CTL encounters an infected cell displaying the viral antigen it's trained to recognize, it binds tightly to it and then delivers a lethal package of cytotoxic proteins, primarily perforin and granzymes. Perforin creates pores in the target cell's membrane.
Punching holes in it?
Kind of, yeah. Allowing granzymes to enter and trigger apoptosis, forcing the infected cell to commit that controlled cellular suicide we talked about with NK cells. These are the true assassins, programmed to find and destroy our own cells that have been compromised and turned into viral factories. They are the surgical strike teams of the immune system, going directly for the enemy's hidden bases, one by one.
And what about the other elite forces being mobilized during this adaptive response? The ones that produce the specialized weapons that can target viruses floating freely in our bodies, preventing them from infecting more cells.
Alongside the activation and proliferation of killer T cells, helper T cells also play a crucial role in activating specific B cells that recognize the viral antigen. This is where the immune system starts mass-producing highly specific soluble weapons.
The antibodies.
The antibodies, exactly. Each B cell has thousands of unique antibody receptors on its surface, and when one of these receptors binds to its specific viral antigen, that's the first step in its activation.
How does that happen? Do the B cells just start firing antibodies immediately?
Not immediately, and this is where the helper T cells come in again, usually. For a robust, lasting antibody response, especially the first time encountering an antigen, the activated B cell needs help from a helper T cell that recognizes the same viral antigen. This T cell help provided through direct contact and cytokine signals.
More cytokines?
Yes, more specific cytokine signals is crucial. Upon receiving these signals, these B cells undergo a significant transformation. They mature and differentiate into specialized cells called plasma cells.
Plasma cells.
These plasma cells are veritable weapons factories, completely dedicated to producing and releasing millions of highly specific protein molecules called antibodies into the bloodstream and tissue fluids.
Millions per second.
Thousands per second per cell. If we connect this to the bigger picture, this is mass production, but with extreme precision. We're talking about millions, billions, trillions of tailored weapons being forged to specifically target this particular viral threat, circulating throughout the body to neutralize free-floating viruses. And the speed and scale of this production, once initiated, is truly astounding.
Okay, so with elite forces mobilize the killer T cells, hunting down infected cells, and millions of highly specific antibodies flooding the battlefield from the B cell factories, the tide of the war begins to turn. But as the source mentions, we have a versatile arsenal of antibodies. Not all antibodies are the same, right? So what does this all mean for how they fight and what unique roles they play in our defense?
You've hit on a crucial point. The source describes a truly versatile arsenal of antibodies. And that versatility comes from their different classes, or isotypes. Each isotype has specialized structural features and therefore specialized roles, maximizing their effectiveness in different battle scenarios and locations within the body. It's a testament to the incredible efficiency and specialization of the immune system.
So let's talk about the specific types. First up, IgM. What's its specialty and what makes it unique?
IgM, or immunoglobulin M, is indeed the first responder antibody. It's structurally unique. It forms a pentamer, meaning 5 antibody units are joined together to form a large, star-shaped molecule.
Like a big snowflake.
Sort of, yeah. This makes it incredibly effective at binding to multiple viral particles. Simultaneously, it has 10 binding sites in total. Because of its large size, it's primarily found in the bloodstream, and it's the first type of antibody produced during an initial infection. Think of it as the initial broad-spectrum strike, acting as an early, potent line of defense in the bloodstream.
So it clumps things together.
Exactly. Its large size and multiple binding sites make it exceptionally good at clumping viruses together, a process called agglutination, which makes them easier targets for other immune cells, like macrophages, to clear. It's like a dragnet, sweeping up as many invaders as possible at the outset.
Okay, so IgM is the rapid initial deployment force, very effective in the blood. What about IgG? I feel like I hear about IgG a lot when people talk about long-term immunity or even maternal immunity passing to babies.
You do, and for excellent reasons. IgG, or immunoglobulin G, is the most abundant antibody in the blood and tissues, comprising about 75–80% of all antibodies, and it's truly the main workhorse of the mature immune response.
Workhorse.
Definitely. Unlike IgM, it's a smaller monomeric antibody, which allows it to readily exit the bloodstream and penetrate tissues, reaching deeper sites of infection. This is like the main infantry, doing the heavy lifting across all terrains. IgG is excellent at neutralizing viruses by binding directly to viral surface proteins, preventing them from attaching to and infecting our cells.
Blocking them.
It also excels at tagging them for destruction, a process called opsonization, where IgG acts like a flag, signaling other immune cells, particularly macrophages and neutrophils, to come and engulf the marked invaders. Critically, IgG is responsible for the bulk of long-term immunity and is the only antibody class that can cross the placenta from mother to fetus, providing passive immunity to newborns.
Ah, that's fascinating. That makes perfect sense for long-term protection. And then we have IgA. The source calls it a specialist in coastal defense. What does that mean, and where does it operate?
That analogy is absolutely perfect, the very vivid description. IgA, or immunoglobulin A, is indeed a specialist in coastal defense because it's primarily secreted across mucosal surfaces.
The wet surfaces, like the inside of your nose or mouth.
Exactly. It's found in saliva, tears, breast milk, and the lining of the respiratory, gastrointestinal, and urogenital tracts. In these secretions, it often forms a dimer, 2 antibody units linked together by a special secretory component that protects it from being broken down by enzymes in these, frankly, quite harsh environments.
Smart design.
Very. Its job is to intercept viruses at their point of entry, preventing them from ever establishing a foothold inside the body. Think of it as having sentinels guarding all the gates and pathways into your body. For example, if you encounter a cold virus by touch and then rub your eye, IgA in your tears would be there, binding to the virus and trying to neutralize it before it can infect the cells of your conjunctiva.
So it stops them right at the door?
That's the goal. This specialized division of labor, with different types of antibodies for different tasks and locations, demonstrates an incredible efficiency, maximizing our defense strategy. Hashtag 4.2, the coordinated 2-pronged attack.
So with all these forces mobilized, these specialized antibodies and the relentless killer T cells, how do they all work together to actually win the battle and clear the infection? It sounds like a highly synchronized operation.
It truly is. This is where the coordination really shines, because the immune system doesn't rely on a single strategy. It's described as a perfectly coordinated 2-pronged attack.
2 prongs, okay.
On one prong, the antibodies, particularly IgM early on and then IgG is the main player, operate in the extracellular space, the fluids between cells, the blood. They clear free-floating viruses circulating in the bloodstream and tissue fluids. By neutralizing them, they prevent new cells from being infected, effectively stemming the tide of the invasion and blocking further viral spread.
So antibodies are like the Air Force, neutralizing enemy units in open spaces, preventing them from ever reaching our cells, our cities. And the killer T cells are assassins. What's their role in this coordinated effort?
The cytotoxic T cells, our assassins, are simultaneously executing the second prong. They are systematically eradicating the enemy's strongholds, which are our own infected cells, those viral factories we talked about earlier. They are the ground troops, or perhaps a highly specialized demolition team, finding those compromised cells and ensuring they are eliminated before they can release more viral particles.
So one stops the spread, the other destroys the source.
Precisely. This combined approach gradually overwhelms the invader. The antibodies neutralize what's outside, while the CTLs destroy what's inside. And finally, once the main battle is won, macrophages, those big eaters, move in again in force to clean up the debris of the battle, ensuring no lingering threats or cellular waste remain. It's a comprehensive approach to overwhelming the invader, leaving no stone unturned in the effort to restore health.
This war, however, is not one-sided. Viruses are not passive targets. They're incredibly sophisticated and engaged in a constant evolutionary arms race with our immune system. This is where it gets truly fascinating, maybe a bit scary. How do they fight back and try to evade destruction, making this an ongoing dynamic conflict?
It's a relentless game of biological cat and mouse, truly. Viruses have developed a dizzying array of sophisticated tactics to evade our defenses, and these strategies are what often make them so challenging to deal with, both for our bodies and for medical science. One of the most common and well-known, particularly for viruses like influenza, is called antigenic drift.
Antigenic drift? That sounds like a shapeshifter, subtly changing its appearance to avoid detection. Can you elaborate on how that works?
That's a perfect analogy. Many viruses, especially those with RNA genomes like influenza, undergo rapid genetic mutations during replication. Their RNA polymerase enzymes, the machinery that copies their genetic material, are notoriously error-prone.
Sloppy copier.
Very sloppy copiers, yes. They make mistakes when copying the viral genome. These small, random errors lead to what we call antigenic drift. They slightly change the appearance of their surface antigens. For influenza, these are proteins like hemagglutinin and neuraminidase, which are the main targets for our antibodies.
So the antibodies don't recognize them as well.
Exactly. The consequence is that antibodies from a previous infection or from a vaccine designed against an earlier strain may no longer recognize them effectively. The virus literally changes its disguise, making our existing wanted posters obsolete, meaning our immune memory, though present, is less effective. This is precisely why we often need a new flu shot every year. The virus evolves just enough to slip past our established defenses. It's a constant moving target.
Beyond changing their appearance, what other sneaky tactics do viruses employ to gain an advantage against our immune system? Do they try to jam our communication lines, for instance?
They absolutely do. Some viruses have evolved to directly attack our communication lines, specifically by interfering with interferon signaling.
The alarm system.
The very first alarm system we talked about. They can actively block the interferon signaling pathways. For instance, many viruses produce proteins that interfere with the host cell's ability to produce interferons in the first place. Or they block the signaling pathways that interferons trigger in neighboring cells, preventing those cells from putting up their shields.
So they cut the wires before the alarm sounds properly.
Precisely. A well-known example is the NS1 protein of the influenza virus, which is a master at interfering with interferon production and signaling. By preventing the alarm from being raised effectively, the virus gains valuable time to replicate and establish a stronger foothold before a robust adaptive immune response can be fully mounted. It's like jamming the enemy's radio signals, blinding and deafening them to the ongoing invasion.
That's incredibly strategic, silencing the alarm to buy time. And what about our highly specific assassins, the killer T cells? Can viruses hide from them too, making their infected cells invisible?
They absolutely can. And this is another example of stunning viral ingenuity. Other viruses can interfere with the MHC presentation system. Remember, the MHC class I molecules are the display stands that present vital antigens on the surface of all infected cells, allowing killer T cells to recognize them.
Right, the ID card showing the viral fingerprint inside.
Exactly. Viruses have evolved diverse strategies to disrupt this. For example, some herpes viruses like cytomegalovirus or CMV produce proteins that literally degrade MHC class I molecules inside the cell or prevent them from ever reaching the cell surface.
So they steal the ID cards, essentially.
Or prevent them from being shown. Without MHC class I displaying the viral antigen, the infected cell effectively becomes invisible to patrolling cytotoxic T cells. This raises an important point. If a cell can't display the viral antigen on its MHC, it's like wearing a perfect cloaking device. The CTLs, despite their incredible precision, can't find what they can't see. This ongoing conflict drives the constant adaptation of both the virus and our immune defenses. It's an endless evolutionary struggle for survival, pushing both sides to constantly innovate.
After the virus is cleared, after the battle has been won and the threat neutralized, our body doesn't just forget everything it learned during the war. This, for me, is the true miracle of immunity, the lasting legacy of the conflict. How do we remember, and what does that memory mean for future invasions?
This is indeed where the immune system truly shines in its long-term sophistication. Right, it doesn't just reset. To conserve energy, because maintaining an enormous army of active T and B cells is metabolically expensive, the vast majority of the activated T and B cells that fought in the battle undergo apoptosis, that programmed cell death once the threat is gone.
They stand down.
They stand down, exactly. They are no longer needed for active combat. However, a crucial subset survives. These are the memory T cells and memory B cells.
So we're talking about the veterans of the war, the ones that have seen combat, have specialized training, and importantly, remember the enemy and the tactics needed to defeat it.
Exactly. These long-lived cells are the veterans of the war. They're numerically smaller than the original activated army, but they are qualitatively superior in some ways, often more sensitive, faster to respond. They retain the specific memory of the viral antigen they were trained to fight. They don't just remember that there was a fight. They remember how to fight this specific enemy, and they do it with greater speed and efficiency. These memory cells circulate silently in the body for years, sometimes even for a lifetime, just waiting, patrolling, ready for a re-encounter with the familiar foe.
It's like keeping a specialized veteran strike force on standby.
That's exactly what it is, ready to deploy at a moment's notice, not just any new recruits.
So, if that same virus dares to invade again years down the line, does our body have to start from scratch, going through that whole dendritic cell migration and T-cell activation again? Or does it deploy these veterans, leading to a much more effective response?
This is the absolute beauty and power of immunological memory. If the same virus ever dares to invade again, these memory cells will recognize it instantly, or at least within hours rather than the days it might take the first time. The response will be far more rapid and powerful than the initial or primary battle.
Much faster.
Much faster and much stronger. Instead of needing days or weeks to mount a full adaptive response, this secondary response happens in a fraction of that time, often peaking within 2-3 days, and with much greater magnitude, more cells, more antibodies.
So it's like going from zero to fully armed and deployed in record time compared to the laborious process of the first infection.
Precisely. Memory B cells, upon re-exposure, are quickly activated and rapidly differentiate into plasma cells, producing a flood of high-affinity IgG antibodies, those workhorse antibodies, but in much larger quantities and often with an even stronger binding capability, better tailored to the invader.
And the T cells.
Memory T cells, both helper and killer types, proliferate rapidly and differentiate into effector cells to orchestrate the response and hunt down infected cells much more quickly. If we connect this to the bigger picture, it's the profound difference between building an army from scratch, recruiting, training, equipping, versus mobilizing a highly trained, experienced unit that is already battle-hardened and knows the enemy.
So this dramatically reduces the time it takes to clear an infection.
Often before you even feel any symptoms. You might get re-exposed to a virus you have memory for and never even know it, because your immune system deals with it so swiftly and effectively. It neutralizes it before it can cause noticeable illness.
Okay, this elegant principle of immunological memory, this ability to remember and respond faster and stronger, is something we hear about all the time, particularly with, well, vaccines. So what does this all mean for public health and how we protect ourselves as a society?
This principle is precisely what is harnessed by vaccines to provide protection without causing disease. Vaccines are, in essence, a brilliant training exercise for your immune system. They introduce a safe, controlled version of a viral antigen, maybe a weakened virus, a killed virus, just a piece of the virus like a protein, or even just the genetic instructions for a viral protein, as with the mRNA vaccines.
Right, different strategies, but the same goal.
Exactly. The goal is to introduce the antigen to your immune system in a way that doesn't make you sick, but does trigger that primary adaptive immune response. Your body learns to recognize the threat and develops those specific memory T and B cells without you ever having to suffer through the actual war first, without the dangers of a full-blown infection.
So it's a brilliant proactive strategy. We're teaching our immune system how to recognize and fight a specific enemy, generating those memory cells and that rapid, powerful secondary response capability, all without the dangerous consequences and potential damage of a full-blown natural infection.
Exactly. It's a proactive defense that prepares your body for future encounters. By activating immunological memory, vaccines enable your body to eliminate a reinfection, or at least significantly blunt its impact, often before you ever develop symptoms. This offers robust protection to the individual and, crucially, significantly reduces the spread of disease within communities, protecting vulnerable people too. It's truly one of the most powerful and successful tools in public health history, leveraging millions of years of evolutionary adaptation to benefit us all. #outtradeontro.
So what does this all mean? We've journeyed through an incredible multi-layered story today, a masterpiece of biological coordination and strategic defense happening right within each of us every single second. An invisible war fought with precision, power, and an astonishing capacity for learning.
It truly is. From the rapid, generalized alarms and immediate responders of the innate system to the highly specific targeted assaults, the intricate cellular communication, the strategic sacrifice, and ultimately the adaptation and long-term learning of the adaptive response. It's an elegance honed by millions of years of evolutionary pressure.
Constant refinement.
Yes, constant refinement, a dynamic and relentless process that silently safeguards our existence, a constant testament to the resilience of life itself.
This invisible war within us, a testament to resilience and sophistication, is truly astounding. As you reflect on this intricate biological battle, consider how these principles, rapid response, specialized defense, constant adaptation, intelligence gathering, strategic sacrifice, and the profound power of memory might apply to other complex systems in your life, maybe your work, or even in society. How do we build systems that learn and adapt as effectively as our own bodies, becoming more resilient and better prepared for the constant, unseen challenges that lie ahead? Thank you for joining us on this deep dive.